Now we will talk about a very important consequence of having energy bands, that is how the electron dynamics gets affected in the presence of electric and magnetic fields, and we will also introduce the concept of effective mass. So we will consider a semi-classical model here. So we will assume that the electronic structure is described quantum mechanically, but the electron dynamics is governed by classical equations of motion, so Newtonian mechanics. So in this model, in the semi-classical model, we assume that the energy bands as a function of the wave vector are known. So we have either measured or calculated the band structure, and we will use this band structure, and we will relate the band structure to the transport properties in response to these applied electric fields and also magnetic fields. The energy dispersion relationship E a sub n of k is basically energy of the nth band. So n is our band index, k is our wave vector, and when we talk about r vector, that is the electron position vector. So in this semi-classical model, we're going to assume that the interband transitions are negligible. So when we apply an electric field, it is small enough that the motion of the electron is confined to a given band. So if we're talking about the electron in the nth band, it will stay in the nth band. It will not have a transition to the n plus 1 band, etc. Now, since the electron motion can be considered as the motion of a wave packet, we will use the group velocity to describe its velocity, and that is basically the derivative of its angular speed omega with respect to k, and omega value depends on which band we are in. So there is the band index n, and also it's a function of k because we have a dispersion relationship. Now the energy of the electron will be given by reduced Planck's constant h bar times omega. So omega is epsilon divided by h bar, it's energy divided by h bar, and therefore the group velocity, which is d omega dk, is 1 over h bar. Now this, what we called epsilon here, will be the energy of the electron in the nth band, so it will be 1 over h bar den dk. Or we can write this as in 3 dimensions. We can write this as 1 over h bar gradient of the energy with respect to wave vector k. Now the work done on the electron by an external electric field in a time interval delta t, work done is the dot product of force with displacement. So it is F dot delta x vector or F dot delta r vector. So this will be the force when we have an electric field E, a constant electric field E being applied. The force on the electron will be minus electron charge E times the electric field E, and since the electron will move parallel to the electric field, the displacement that we have in a time interval delta t is its group velocity multiplied by delta t. Now, this small change in the energy, delta epsilon or delta E, is dE dk delta k. So the derivative of energy with respect to the wave vector k, that is basically h bar times the group velocity. So we can substitute that here. And h bar times group velocity times delta k will be equal to the work done on the electron minus EE group velocity delta t. Group velocities will cancel, and we will find that h bar dk dt is equal to minus electron charge times electric field E, which is our force F. So we find that the force is given by derivative with respect to time of h bar k. So it's h bar dk dt. So we can recognize the momentum of the electron to be equal to h bar k. Now the free electron velocity, we can check from this. It is going to be 1 over h bar derivative with respect to wave vector k of the free electron energy h bar square k square over 2m. The derivative will give us 2k, so it will be 2h bar square k over h bar 2m. H bar will cancel one of the h bars in the numerator, so we will have the 2's cancelling, and we find that the free electron velocity is h bar k over m, which is its momentum divided by m. So we find that in the case of the free electron, the group velocity increases linearly with the wave vector k. If we have an applied electric field, a constant electric field in r hat direction, the force on the electron h bar dk dt is minus EE0. That gives us, for the solution of the wave vector k, k0 minus EE0 over h bar t. So it's changing linearly with time, and since the group velocity will be h bar k over m, it's h bar k0 over m minus EE0 over mt. So we find that it is v0 plus at, acceleration times time. So it's basically linearly changing with time. Now, for the case of the Bloch electron, when we have this band structure, you can see here, we have a band gap, as you remember. So this is just the first band that I have drawn here for the one-dimensional case. If you look at the derivative of the energy with respect to the wave vector k, you can see that we will obtain this 1 over h bar times this derivative gives us the velocity of the electron. So this suggests that the velocity of the Bloch electron increases as k increases up to a certain point, and then it starts decreasing. So there is deceleration opposing the electric field, and actually the velocity of the electron becomes zero when we reach the zone boundary where we have the Bragg reflection condition satisfied and we have standing wave solutions. Okay, so unlike the free electron case, the velocity and energy are oscillatory in k, because if you go to the next band and reduce it to the first Brillouin zone, if you remember, we will have this band gap and then the next band forming like this. So it's going to be oscillatory in the energy and also in the velocity. So this is a striking difference between the free and the Bloch electron. So the fact that this velocity changes as we approach the zone boundary is a striking difference. It basically decreases. So the velocity is linear in k near the band minimum, so it behaves like a free electron near the band minimum. However, it reaches a maximum close to the zone boundary and drops to zero at the zone edge. So we have this important difference. Now, when we apply a magnetic field, on the other hand, we have the Lorentz force acting on the electron. It is QV cross B. The charge of the electron is minus E, so it is minus EV cross B, which is our force h bar dk dt. And the velocity is the group velocity, which is 1 over h bar dE dk. So we find that dk dt is minus E over h bar square, gradient of energy with respect to k, cross product with magnetic fields. Now, what does this equation tell us? It tells us that the electron moves in a direction that is normal to the gradient of energy. That means the electron is moving on a constant energy surface. So the energy of the electron does not change when you apply a magnetic field. A plane perpendicular to magnetic field intersecting the constant energy surface will give us the electron trajectory. So it will move on this trajectory which is perpendicular to the energy gradient and magnetic field, which is the constant energy surface that is intersecting the plane perpendicular to the magnetic field. That gives us the trajectory. Now, last but not least, we have another important concept that comes out of this model, that is the effective mass. Now, using Newton's second law of motion, the net force acting on the electron should be equal to its mass times acceleration. In this case, we will call this mass effective mass, and we see that this net force that we apply, which is dp dt or h bar dk dt, will be equal to m star dv dt. So for the group velocity, we substitute 1 over h bar gradient of energy, or dE and dk, for the nth electron in the nth band. We will have h bar times delta k is equal to m star over h bar den dk. Therefore, you can see that what I'm calling the effective mass here, m star, is h bar square 1 over the second derivative of the energy with respect to k. So this is for the electron in the nth band. Okay, so the black electron has an effective mass, and if you write the three-dimensional version of this equation, it is h bar square divided by the second derivative of energy with respect to k, del square k. So this is determined basically by the curvature of the energy band it resides in. Okay, so what does that mean? If I look at an energy band diagram, so I see a large curvature here. If you have a large curvature, the second derivative is large. That means we have a light electron. M star will be small. On the other hand, if we have a small curvature, that means we have a heavy electron. So looking at this energy band diagram, I can see the effective mass of the electron by looking at the curvature. Now, since in general the dispersion relation depends on the crystal direction, the effective mass also depends on the crystal direction. So we plot this for a certain k wave vector direction. It can be 1, 0, 0, 1, 1, 1 direction, etc. And we have different energy bands in different directions. So therefore, the effective mass depends on that crystal direction. Now, in general, the effective mass is a tensor. It is basically given by 1 over m star mu nu is equal to 1 over h bar square d square e dk mu dk nu. So mu and nu are our Cartesian coordinates. So that's the generalized effective mass. So end of the story, an electron in an energy band responds to electromagnetic forces as if it had an effective mass m star. So in summary, we have seen that the velocity of the electron using a semi-classical model where we have the energy band structure calculated or measured that is determined by quantum mechanics, the electron itself is obeying Newton's laws of motion, classical mechanics. We see that the group velocity of the electron is given by 1 over h bar gradient of energy. The momentum is given by h bar k, and we have checked the situation for the free electron case, where we find that when you apply an electric field to a free electron, its velocity will be changing linearly with time, whereas for the black electron, the situation is quite different. When the wave vector increases to a value close to a zone boundary, the velocity actually quickly decreases down to zero, where we have the standing wave solution. So that's a striking difference between these two. On the other hand, in a magnetic field, we see that the electron energy doesn't change. dk dt is minus e over h bar square gradient of energy cross product with magnetic field. The electron moves on a trajectory that is simultaneously perpendicular to the magnetic field and the gradient of energy, which means the electron is moving on a constant energy surface. The application of the magnetic field does not change its energy. On the other hand, using Newton's second law of motion, we see that the effective mass of the electron is given by h bar square 1 over second derivative of the energy of the electron with respect to the wave vector k, so the effective mass is determined by the curvature, and the curvature changes with direction, so effective mass is direction dependent. So the electron behaves, or we can use the semi-classical model that takes into account the energy band structure and Newton's second law of motion if we introduce the concept of effective mass, and the effective mass of the electron that is determined by the curvature of the energy bands.